So, what if the most fundamental aspect of our universe isn't some exotic new particle or a strange undiscovered force? What if it's something so huge, so ever present, that we've just been looking right through it the whole time? In this explainer, we're going to dive into a radical idea that could completely change how we see everything. And it all starts with the very nature of empty space. Right, we're all taught to think of the vacuum of space as, well, nothing, the ultimate void. But is that really true? I mean, what if the absence of stuff doesn't mean the absence of everything? This simple question, it turns out, is at the very heart of a huge new challenge to modern physics. There's this new framework called dynamic vacuum field theory, or DVFT for short, and it says the vacuum isn't empty at all, not even close. It suggests space itself is a real physical medium, a kind of substrate that everything else exists in. And if that's true, the reason we've missed it isn't because it's not there, but because the tools and methods we're using are just completely wrong for the job. So part one, looking for the wrong thing. The first big reason we might have missed the boat on this comes down to a really simple but totally critical mix-up. Modern physics is unbelievably good at finding particles. Think of it like this. We're expert fishermen. We can find any fish swimming in the ocean. But this theory, DVFT, argues that the vacuum isn't another fish we need to catch. No, it's the ocean itself. So all of our amazing scientific tools, they're like these incredibly advanced fishing nets. They're designed to catch things, but they're totally useless for actually catching the water they're being dragged through. And that's exactly why even our most powerful machines, like the Large Hadron Collider, would probably be completely blind to a vacuum substrate. See, colliders are built to find new particles. They're looking for these sharp, clear spikes in the data. But if you poke and prod the very medium of space itself, what happens? Well, it might just respond by creating particles we already know about. Or it could produce these tiny, smeared-out effects that are so broad they just get dismissed as background noise. We could be testing the vacuum all the time, but we're just interpreting the results in the only language we know, the language of things that exist in the vacuum, not the vacuum itself. Okay, part two. Evidence in disguise. So if our labs can't see it directly, does that mean it's a dead end? Well, not so fast. This theory suggests the evidence has been staring us in the face for decades. We've just been calling it by a bunch of different names. Take a look at some of the biggest head-scratchers in cosmology. That weird way galaxies rotate that makes no sense. We invented a whole new thing, dark matter, to explain it. DVFT says it's actually just the vacuum responding to gravity. The universe expanding faster and faster, we call that dark energy. DVFT says no, that's just the vacuum's own internal dynamics at play. The insane expansion of the early universe, we use a theory called inflation. DVFT points to the vacuum's original state. All of a sudden, you've got three of the biggest puzzles in science, and they might all be explained by one single underlying thing. So you might be asking, why would these effects only pop up on a cosmic scale? Well, it's because the vacuum's properties are probably incredibly subtle. In a lab experiment, any effect is so tiny it's basically negligible. But stretch that out over galactic distances and over billions of years, and those tiny persistent effects start to add up. They accumulate and eventually become the dominant force in the system. It's kind of like gravity, right? It's the weakest force we know, but at the end of the day, it's what shapes the entire cosmos. So if the evidence is there, why haven't cosmologists spotted it? The problem is that the standard model of cosmology is, well, it's really flexible. You can add things to it like dark matter and dark energy and just adjust the dials until it fits what we see. So the model sees the vacuum's effects, sure, but it just gives them a different name, effectively hiding what might really be going on. Part 3, a new kind of proof. All right, if we can't just find it with a particle detector, how could we ever actually prove this thing is real? It turns out it just requires a different way of thinking about scientific proof. The key here is an idea called indirect inference. And this isn't some weaker form of science either. It's how we already know about some of the most fundamental things in the universe. I mean, think about it. We don't directly see the curvature of space-time. We infer it's there because we see its consistent effects everywhere we look, like how light bends around stars and how clocks tick differently in a gravitational field. The argument is that we need to apply that exact same logic to the vacuum. And this leads us to the real nail-biter, the fixed parameter test. This is what makes the theory testable, what makes it real science. Here's how it works. First, you figure out the vacuum's fundamental properties, its density, its stiffness, whatever they are, by fitting them to data from one area, say how galaxies spin. You get your set of numbers. Then, and this is the absolutely crucial part, you take that exact same set of numbers, no changing them, no tweaking, and you use them to predict something in a completely different area of physics, like a really specific effect in a quantum mechanics experiment. If those predictions match, wow, that's powerful. That is some serious cross-domain evidence that you've stumbled upon a single underlying reality. So let's bring this all home. Part 4, why this was missed. How on earth could all of modern physics overlook something so incredibly fundamental? Well, it wasn't just one thing. It was kind of a perfect storm of factors all converging. We are particle hunters, but this thing is a substrate. Its fundamental properties are way too subtle for our lab gear to measure directly. In our experiments, its tiny effects just get filtered out and ignored as noise. Meanwhile, in cosmology, where the effects are huge, they get slapped with other labels, like dark matter and dark energy. And on top of all that, there's this historical bias. Ever since the old ether theories were disproven a century ago, any idea that smells like a physical vacuum has been treated with a whole lot of suspicion. Honestly, the best summary comes right from the source material. It argues that the dynamic vacuum stayed hidden because it would not appear as a new particle, but as a tiny universal background, easily absorbed into existing theories. It's been hiding in plain sight the entire time. And that leaves us with a pretty wild final thought. You know, we've spent 100 years searching for the ultimate actors on the cosmic stage, the most fundamental particles. But what if the greatest discovery left to make isn't another actor at all, but the stage itself?